All right, I'm going to talk about the convexity bound, which is a bound that's used for bounding L functions in the critical strip along vertical lines. So the starting point is what's called the Fragment-Lindelof principle. So Fragment-Lindelof. And the for precise statement, I'll give as reference Goldfeld's book, Automorphic Forms and L Functions for the group GLNR. So for short, I'll just write GLNR, and it is section 8.2. So the Fragment-Lindelof principle says that if you have some function phi, which is holomorphic on some strip, say sigma 0, sigma 1. So here when I write sigma, I'm always taking some complex number s to be sigma plus it. So unless the context suggests otherwise, sigma is always the real part of some complex number, and t is always the imaginary part. So you've got phi, it's holomorphic in some strip, and also want that that phi doesn't grow too quickly as the imaginary part goes to infinity. So here, polynomial growth is sufficient. You can be a little bit more lenient than that if you want to, but this isn't really gonna. We're not really gonna have to worry about this. And then the idea is that say that the absolute value of phi on the line with real part sigma 0, so at the left edge of the strip, is less than I'll just write less than t to the m0, and similarly on the right edge of the strip, it's going to be also bounded by some power of t. And this is as t is going to infinity. And then the theorem essentially says that for some intermediate real part, is going to be less than some power of t. And here the power of t is it's what you get if you linearly interpolate. So let me draw a picture to illustrate this. So this is going to be real part sigma 1. This is going to be real part sigma 0. And here you have this vertical axis, and I'm going to say this is going to be m0, and it's going to be m1. So this is the power of t that is bounding the growth on this vertical line. And what you do is you linearly interpolate. And then if you have some sigma in between, you just see where you are on this linear interpolation. And this will be your m. So I'll write this m. So what is m? M is going to be, I guess, m0 times sigma minus sigma 1 plus m1 sigma minus sigma 0 over sigma 1 minus sigma 0. Is this right? So when this is sigma 1, you get the right thing. And when this is sigma 0, you get minus the right thing. Is that right? Yeah, so we'll probably need a minus sign here. Okay, cool. So this is the statement of Fragment-Lindelof. Again, I may be skipping a few technical details, and I give this reference, this textbook, if you want to sort of dig into the nitty-gritty or if you want a proof. But this is the idea, that if you have a bound on two vertical lines, then you linearly interpolate, and that bounds in between. Okay. And this is a generalization, essentially, and it's not literally a generalization, but it's thought of as a generalization of the maximum modulus principle. So this is a similar statement that we're not really going to make use of, but it inspires and contextualizes the Fragment-Lindelof principle. So this is if F is holomorphic on some set, whatever, then the idea is you take some point Z naught, and then you look at some neighborhood of Z naught. So I'm just going to call this U for, this is the neighborhood of Z, and this is open. And F is assumed to be holomorphic on U. Then the statement of the maximum modulus principle is that if the modulus of F at Z naught is greater than or equal to is equal to the max of, for Z in U of the modulus of F, then that implies that F is constant, which is, this is a very powerful statement, right? This is this is not, you wouldn't expect a normal function to have this, right? So holomorphicity is actually a very stringent condition. And so the idea, the way that people normally think about this, or at least the way that I normally think about this, is that, it's all right, sort of quasi-equivalence, is that so F attains maxima only on the boundary of these open sets, right? So if you have a maximum sort of, sorry, maybe the absolute value, right, attains maximum only on the boundary. So the maximum modulus of a holomorphic function on some compact region, connected compact region, has to be on the boundary of that region, and this is universally true. And this holds for compact regions. Well, sorry, I mean, it's assumed to be open, so it can't be compact, bounded maybe. And so the Fragment-Lindelof principle, right, this is operating in some vertical strip, right? So as the imaginary part goes to infinity, so it's not some bounded region. So you can't apply the maximum modulus principle, but in spirit, the Fragment-Lindelof principle is the maximum modulus principle on vertical strips. Okay, so why do we care about the Fragment-Lindelof principle? Well, it's because of something called the convexity bound. And this is the main thing to take away from this. So for this, it's still the same reference. Goldfeld's book, Automorphic Forms and L Functions for the group GLNR, section 8.2. Specifically, it's theorem 8.2.3. So let me just state this, and then we'll talk about it. So you've got some L function, L of S, and this L function is going to satisfy a functional equation. So we've got functional equation, and the functional equation I'm going to write as uppercase lambda of s, which I'm defining to be, it's going to be n to the s for some n, and then you're going to have a product j from 1 to lowercase n of some product of gamma functions. So here's got lambda s or some lambda plus mu j. So this is just what a functional equation, we're assuming the functional equation looks like, and then we're going to normalize it so that this is the analytic normalization for L functions. We're going to normalize it so that it's s to 1 minus s. And Goldfeld writes it this way, so I will too. And here w is this root number, has absolute value 1. And so we're assuming that the L has this functional equation. And here, the lambdas have to be positive, etc. You can get an exact statement for what all these things are in Goldfeld's book. And we're also going to assume that L has a pole of order lowercase l. Maybe I won't use lowercase l because it's not so clear visually. So of order m at s equals 1. Then this is the convexity bound. And it is just applying the Fragment-Lindelof principle to lambda, essentially. What we get is that the absolute value of L is going to be less than or equal to C sub epsilon. So this epsilon is an arbitrary positive real number, and C sub epsilon means that there's a constant that depends on your choice of epsilon. And then what you have is you have n times the product, j from 1 to n of 1 plus the absolute value of lambda. So this lambda is the lambda that appears in the gamma factor. And then t is the imaginary part of s. And then here you have this is going to be the imaginary part of mu j, all to the power lambda, and then all of this to the power 1 minus sigma plus epsilon. So here's where the epsilon comes up, right? You can't quite bound it by the thing you get from linearly interpolating, but you have an epsilon, and then if you want to make this epsilon small, you have to you might need a different constant, but in practice this epsilon is fine. Okay, so this is sort of a more massive notation, but it's really just exactly what you get when you apply the Fragment-Lindelof principle with the functional equation, right? Because the key idea here is that for L, if you look at L at 1 plus epsilon plus it, then this is bounded, right, as a function of epsilon, because here what we're doing is we're assuming that this L function converges absolutely when the real part of s is greater than 1. This is sort of what's meant by the analytic normalization. So when you're applying the Fragment-Lindelof principle, you have, say, 0 over here, and then you have 1, and this is your sigma. And over here, when you're at 1 plus epsilon, the power of t that appears in the growth along a vertical line is 0, right? Because if you just look at, say, a series definition, for L of S, then you can take absolute values, and the absolute value of this is just by the triangle inequality less than or equal to the sum n from 1 to infinity of an over, and taking these absolute values is fine. You still converge because it's assumed that L converges absolutely, and here you just have an n to the sigma, right? So essentially there's no possible growth if you converge absolutely as t goes to infinity. So here you're guaranteed to have this is the m1, the uppercase m1 from the Fragment-Lindelof principle over here. This is maybe the sigma 1, and this will be your sigma 0. And then to get the other one here, you use the functional equation, and you get what this thing is. And then you can imagine that, so you get some m0 from the functional equation, and then you can see that this 1 minus sigma, this is really just what you get from this linear interpolation, and the epsilon comes from the fact that you're not quite at 1 for sigma 1, you have to be a little bit past it, right? This is this epsilon. Okay. So this convexity bound, it's really just a direct consequence of the Fragment-Lindelof principle, and for details you can check Goldfeld's book. Okay, so let me give an example. So the Riemann zeta function satisfies a functional equation. So the functional equation is, let me write pi to the s over 2 gamma of s over 2 zeta of s. I believe this is right. Let me check very quickly. Yeah. Minus s over 2. And then we're going to define this to be lambda of s. And then this is equal to lambda of 1 minus s. This is the functional equation. Okay. So comparing to the statement of the convexity bound, right, we're going to, the power of t that we're getting, ultimately, if let's not care about the other variables for now. The power of t that we're getting is going to be t to the lambda, where lambda is the coefficient of s appearing in the gamma factors. And we also have this pole at s equals 1, so you might have to care about that, but I'm just going to look at it as t going to infinity, so that factor tends to 1. So the convexity bound is that the absolute value of zeta of s in the critical strip is less than, and then here we have a t to the, so again, it's lambda times 1 minus sigma plus epsilon, so it's going to be 1 minus sigma over 2, because lambda is 1/2 here. This is lambda. 1/2 is lambda. So, and then the plus epsilon. Okay. So this is what the convexity bound gives you for the zeta function. So, for example, this tells you that on the critical line, zeta 1/2 plus it, and this is as t goes to infinity. When t is going to 0 or something, you can't conclude that your thing is 0 here. This is telling you that the zeta function is less than t to the 1/4 plus epsilon. Right? So you plug in sigma is 1/2, you get 1/2 over 2 1/4. And this is for sigma between 0 and 1. Okay. So that's what the convexity bound would give you for the zeta function.